Welcome, fellow chemists, to the 5th video on the reactions of the alkynes. We're almost at the end of the alkyne series, so please send me suggestions for future videos. Today we will take a quick look at the addition of halogens. Why a quick look? Because if you have watched my previous videos, I will not actually mention anything truly new or that unusual. The basics are, unsurprisingly, exactly the same if the ratio of halogen to alkyne is 1:1. The reaction takes place in dichloromethane like before, and we simply add across the triple bond to get a dihalide product. So is there any difference? Well, with alkenes we can identify the isomer. With a single addition, the dihaloalkene will always be a trans E isomer. The current product I have drawn does a poor job of representing this. So if I switch one of the bromine's locations, then it kind of implies the trans isomer. Of course, I can draw the product differently again, and this may be the clearest. If there is originally an excess of bromine or we decide to add more, the reaction repeats and we get a tetrahalide product. Interestingly, after bromination, you could choose to add a different halide like chlorine. There is no trans or E designation for tetrahalides. So do multiple products pop up here due to differences in symmetry? With symmetrical alkynes, we add the same substituent with the first addition, and then again if there is a second. In both cases, we get only one product. With asymmetrical alkynes, the process is the same where we add identical substituents once or twice, so we still only get one product. We encountered multiple products previously because different substituents like H and OH were added to the carbons. Speaking of H and OH, you might remember that halogen addition does not only take place in dichloromethane. If you watch the reaction with alkenes, then you'll know that if water is present, a halohydrin can form. When it takes place on an alkene, we get a halogenated alcohol, but on alkynes, we get a halogenated enol. For those who watched the previous two videos, you already know an enol will rearrange into a ketone, which in this case happens to be halogenated. For a symmetrical alkyne, there will be only one product, as no matter how we draw it, the name doesn't change. Do you think it is different for asymmetrical alkynes? Give it a go and develop the structure and name. The addition is simple enough, but after tautomerization, we have to consider the positions of the ketone and halide in order to name it properly. In this case, we do get two different structures. I do plan on naming ketones in more detail in a future video, so as the briefest of spoilers, we prioritize the keto group, then name the rest of the molecule accordingly. In summary, for internal alkynes regardless of symmetry, a single addition results in a trans E dihalide product. For a terminal alkyne, the dihalide can only be classified as E. Unlike alkenes though, this addition can happen again with the same halide or another and result in a tetrahalide product. In the case of internal alkynes, the symmetry makes no difference, there is only one product. For terminal alkynes, if there is two equivalents of one halide or a mix of two, there is only one product in each case. If the reaction takes place in water, a symmetrical alkyne produces a halogenated ketone. If the alkyne is asymmetrical, there is the potential for two ketone products. If the alkyne is terminal, we get a ketone with the halide on a primary carbon. Coming up, it is time to finish these basic reactions with hydrogenation. Thank you very much for watching. If you enjoyed this video, please like and subscribe as I have more in development. All that's left is hydrogenation, and here's the process with the alkenes.